So the structural features, to summarize then, chains are divided into domains. The light chain has one variable and one constant domain. Heavy chains have one variable and 3 or 4 constant domains, called CH1, 2, and 3. Heavy chains are named by Greek letters that correspond to the name of the class. If you see any time somebody writes a comment or a question, for example, about antibodies, and you see a Greek letter, what you need to realize is you're not looking, they're not asking about the entire antibody molecule, they're asking about one chain of the molecule. The whole molecule would be called IgG, or IgM, or IgA. The heavy chain of that molecule would be named by the corresponding Greek letter. Gamma for IgG, which is Greek for G, delta for IgD, mu for IgM, alpha for IgA, and of course epsilon for IgE. Light chains also have Greek letters that describe them when you're talking about a light chain only, called kappa and lambda. Each domain is about 110 amino acids long with a single intrachain disulfide bond. Now, that's not a number I expect you to remember. It's not going to be a big deal, but I would like you to keep it in mind at least throughout the day-to-day, just through this morning, because I'm going to use that number when we describe some of the characteristics of how the genes that encode for these molecules actually are expressed. So when we draw antibodies, they're typically drawn like this, showing the stick figures. The disulfide bonds hold the heavy chains together. The domains are the little block-like structures, and the binding site for antigen, where it actually contacts antigens, up at the top, which is the amino terminal end. So heavy and light chains are highlighted on the picture on the right, or on the left rather, and on the right you have the variable regions differentiated from the constant regions, both for heavy and light chains, just to illustrate the functional separate regions of the antibody molecule. This gives you an idea of what it really looks like in real life. The important things that we've learned about antibody to relate its structure to its function is based upon a dissection of antibody molecules using enzymes. Fragments of degraded antibodies are produced by enzymatic degradation. These are not functions that occur in the body. These are not physiologically significant. These are test tube experiments only. However, the nomenclature that comes from antibody degradation and the fact that it can be used to establish the relationship between structure and function is important to know. And although these are old experiments that were done many, many years ago, they still ask about them on exams. Maybe our exam, the step 1 exam, definitely still asks about these. Doesn't matter that the experiments are 40 or 50 years old now. Degradation of IgG antibodies, which are illustrated here, with the enzyme papain. Papain cleaves where those red daggers are, in the hinge region above the disulfide bonds that hold the heavy chains together, creating 3 fragments. 2 of them are identical and are called FAB. That stands for fragment antigen binding. FAB, fragment antigen binding, because they still have antigen binding sites right up here at the top of the molecule. There's your binding site right here, and another one right here. The valence of IgG is 2. One IgG can bind 2 antigens. The valence of the FAB fragment is 1. Each fragment binds 1 antigenic site, right there and right there. The piece left behind is called FC. That stands for the fragment of the constant region. It really got its name for a different reason, because when the experimenters first did this degradation and purified the different fragments, they found out that the test tubes that contained the FC fragment formed crystals quite easily when it sat in the cold room overnight. So they called it the fragment that crystallized, or FC, fragment crystallizable. The reason they crystallized was because they were from the constant region of the molecule, So they all had the same amino acid sequence, so they could form regular crystals rather easily, and that's exactly what they did. Now, in contrast, if you degrade antibody with the enzyme pepsin, pepsin cleaves where all the red daggers are in the lower panel, chewing the Fc region up so badly that they don't even have names for it. They're just called fragments. So they get completely fragmented and digested. It leaves behind one big fragment called FAB'2. That stands for fragment antigen binding, and there are 2 binding sites on the fragment. It still has a valence of 2, like antibody, because this is all one structure. The disulfides hold it together, and it's still got 2 binding sites on the fragment. Now, of course, one of the keys to get those kind of questions right is you have to remember which enzyme causes which produces which fragment. And pepsin and papain sound a lot alike. So you're going to have a foolproof way of remembering which one is which. Now, I've taught this stuff for like 40 years. So, and for the longest time, I never memorized which enzyme created which fragment, because I didn't have to. I always had a diagram like this right in front of me. So I could say, and so of course, pepsin generates an FAB'2 fragment. Sounds like I know what I'm talking about, right? But I peeked. Well, if you're taking an exam, you're not going to have a nice diagram like this all labeled in front of you. You're going to have to remember. So you got to have a mnemonic to remember. Boy, do I have a good mnemonic for you. This one works every time. Pepsin, as you can see in the picture, generates an FAB'2 fragment. That looks like a cup, doesn't it? Pepsin generates, get ready for this now, this is really bad. Pepsin generates a Pepsi cup. Pepsin generates a Pepsi cup. Here it is filled with Pepsi. Watch the screen. Here it goes. There you go. That's your Pepsi. So it's a cup, like it's got a bottom on it. So you can remember that pepsin generates an FAB'2 fragment. Whereas if you tried that with papain, the Pepsi would just run all over the screen. So that's one way to remember which enzyme creates which fragment. It's foolproof. I got to tell you.